In the year 2120, humanity stood on the edge of a planet that had once been nothing more than a distant red point in the night sky. Mars, cold, dry, and hostile for billions of years, was no longer just a destination for probes and short-term missions. It had become a project measured not in decades but in centuries, a deliberate effort to reshape an entire world using patience, physics, biology, and sacrifice. Terraforming was never imagined as a single dramatic moment, but as a slow accumulation of changes, each one grounded in principles understood long before the first permanent settlement was established. Mars presented enormous challenges from the beginning. Its gravity was only about 38% of Earth's, which meant a thinner atmosphere could not be held as tightly. Its magnetic field had largely vanished billions of years earlier, allowing solar radiation to strip away gases over time. Average surface temperatures hovered far below freezing, and liquid water could not remain stable for long. Any attempt to transform the planet required working with these constraints, rather than pretending they did not exist. The earliest phase of terraforming focused not on people, but on infrastructure. Automated factories spread across the surface, extracting carbon dioxide from the polar ice caps and regolith. This gas, already present in large quantities, became the primary tool for warming the planet. By releasing it into the atmosphere, engineers increased the greenhouse effect, a method well understood from climate science on Earth. Each incremental rise in pressure and temperature was carefully monitored, because runaway effects could not be allowed. Orbital mirrors played a crucial role during this period. Positioned at stable points in space, they reflected additional sunlight onto specific regions of the planet, particularly the poles. The goal was not to scorch the surface, but to gently encourage sublimation of frozen carbon dioxide and water ice. This technique relied on basic optics and energy balance calculations refined over generations. As more gas entered the atmosphere, surface pressure slowly climbed from less than 1% of Earth's toward levels that allowed new chemical processes to begin. Water was always central to the plan. Mars already held vast reserves locked in ice beneath the surface and at the poles. As temperatures rose, seasonal melting became more pronounced, creating transient flows that reshaped the landscape. Channels carved by ancient rivers, long dry, began once again to guide moving water, if only for part of the year. These early flows were unstable, but they marked a turning point, proving that liquid water could exist beyond sealed habitats. Radiation remained a constant threat. Without a global magnetic field, the surface was exposed to cosmic rays and solar particles. The solution was not a single shield, but layers of protection. Thickened atmosphere provided some defense, while strategically placed electromagnetic generators near key settlements created localized fields. These systems were based on principles of plasma physics and electromagnetism tested in space decades earlier. Over time, they reduced radiation levels, enough for limited outdoor activity with protective gear. Biology entered the equation cautiously. The first living organisms released onto the planet were not plants or animals, but engineered microbes. Designed to survive extreme cold, low pressure, and high radiation, these organisms consumed carbon dioxide and released oxygen through photosynthesis. Similar extremophiles already existed on Earth in harsh environments, proving that life could adapt given the right tools. On Mars, their spread was controlled and monitored to prevent unintended consequences. Oxygen levels rose slowly, far too slowly for human breathing, but enough to begin altering surface chemistry. Oxidation processes changed the color and composition of rocks, while trace ozone formed in the upper atmosphere, offering additional radiation shielding. Every change was incremental, measured in fractions of percentages, yet each step built upon the last. Terraforming was understood as a chain reaction, guided rather than forced. Soil development posed another challenge. Martian regolith lacked the complex organic structure of Earth's soil and contained perchlorates toxic to most known life. Microbial processes were again employed to break down these compounds over time. Organic material imported from off-world waste recycling systems added carbon and nitrogen, creating the beginnings of a living substrate. This was not farming as it was once known, but the foundation upon which future ecosystems could be built. Energy demands were immense. Solar power was abundant but inconsistent due to dust storms that could last for months. Nuclear reactors provided a stable baseline, drawing on designs that prioritized safety and longevity. Heat generated by these systems was not wasted but redirected to maintain subsurface water reservoirs and industrial processes. Energy planning was as critical as atmospheric engineering because without it, progress would halt. Psychological factors were also considered, even in this early phase. Living on a transforming planet required a shift in perspective. Settlers knew they would not see the final results of their work. This understanding was built into governance and education, emphasizing stewardship over ownership. The idea was not to conquer Mars, but to collaborate with its environment using knowledge accumulated over centuries. By 2120, the atmosphere was still unbreathable, without assistance, yet pressure had increased enough that exposure no longer meant instant death. Water ice melted more readily, and clouds occasionally formed thin and pale against the sky. These clouds represented a milestone, indicating active weather cycles, however weak compared to Earth. Each observation reinforced the idea that planetary scale change was possible given time. The timeline remained long. Estimates suggested that achieving an atmosphere comparable to Earth's would take many hundreds, if not thousands of years. Loss to space would always be a factor, requiring continuous replenishment. Terraforming was therefore not a finite project, but an ongoing commitment. This reality shaped every decision, ensuring that systems could be maintained and adapted by future generations. Technological redundancy was built into all major systems. Factories, mirrors, generators, and habitats were designed to fail gracefully rather than catastrophically. Lessons learned from early space exploration disasters informed every protocol. Mars offered no room for complacency. Dust infiltration, temperature extremes, and mechanical wear tested equipment relentlessly. Maintenance became a defining feature of daily life. Communication delays with Earth reinforced autonomy. With signals taking several minutes each way, local decision-making was essential. Scientific models guided action, but real-time adjustments depended on observations made on site. This separation fostered a distinct culture focused on resilience and long-term thinking. Policies were debated not in terms of years, but in terms of centuries. As the planet warmed, carbon dioxide levels eventually approached a point of diminishing returns. Additional greenhouse warming required new methods. Methane production was explored using controlled biological and industrial processes. Methane, being a more potent greenhouse gas, offered increased warming with smaller quantities. However, its instability required careful management to avoid rapid breakdown. Atmospheric chemistry simulations guided deployment, ensuring balance rather than excess. Cloud seeding experiments began cautiously. Introducing particles to encourage condensation helped distribute heat more evenly across the planet. This reduced temperature extremes between equatorial and polar regions. The goal was not to mimic Earth exactly, but to create a stable environment capable of supporting complex life. Stability mattered more than familiarity. Oceans were never part of the near-term vision. Mars lacked enough accessible water to cover its surface deeply without massive importation. Instead, networks of lakes, seas, and underground reservoirs were planned. These bodies of water moderated local climates and supported biological activity. Their placement followed topography identified through detailed mapping long before terraforming began. Dust storms remained a defining feature of the planet. Warming increased atmospheric activity, leading to more frequent storms. Rather than attempting to eliminate them, planners adapted. Structures were shaped to reduce accumulation, and energy systems accounted for reduced solar input. Storms became part of the rhythm of the planet, a reminder that control was always partial. Gravity posed biological concerns. Long-term exposure to lower gravity affected muscle bone density and cardiovascular health. Medical research, ongoing for more than a century, informed countermeasures, including exercise regimes and pharmaceutical support. Genetic adaptation was debated ethically and scientifically, but remained limited. Terraforming focused on the planet, not redesigning the human body. By this stage, experimental plants were introduced within protected environments open to the atmosphere, but shielded from radiation extremes. These plants were descendants of hardy species selected for low light tolerance and cold resistance. Their success varied, but each generation offered data. Photosynthetic output increased oxygen marginally, while roots contributed to soil structure. Life was beginning to leave a visible mark. public perception beyond Mars fluctuated. Some viewed the effort as essential to long-term survival, while others criticized the resources required. These debates influenced funding and policy, but the project continued, sustained by its momentum and the people committed to it. Terraforming had become more than science, it was a statement about intent. Scientific instruments tracked atmospheric loss to space constantly. Even with increased pressure, particles continued to escape, driven by solar wind. Proposals to generate an artificial magnetic field at a planetary scale were studied. Concepts included placing a powerful magnetic source at a stable orbital point to deflect solar particles. While technically feasible, the energy requirements were enormous, making it a long-term goal rather than an immediate solution. Education on Mars emphasized systems thinking. Children born there learned about feedback loops, atmospheric chemistry, and ecology as practical knowledge rather than abstract theory. The planet itself was the classroom. Every change observed outside reinforced lessons about cause and effect. This approach ensured continuity of understanding across generations. Economic systems adapted as well. Traditional scarcity models shifted toward resource cycling and reuse. Importing materials from Earth was expensive and slow, so local production became essential. Mining focused on elements required for construction, electronics, and life support. Waste was treated as a resource, closing loops wherever possible. These practices supported terraforming by reducing environmental strain. Cultural expression reflected the environment. Art, music, and storytelling often centered on transformation, patience, and scale. The red landscape, slowly changing hues under thin clouds, inspired new aesthetics. These expressions reinforced communal identity and purpose. Terraforming was not just engineering, but a shared narrative. As pressure increased, simple liquid water systems became more reliable. Open channels lasted longer during warmer periods, feeding reservoirs and supporting microbial mats. These mats darkened the surface, absorbing more heat, creating localized warming. This positive feedback was encouraged in controlled regions, demonstrating how biology and physics could cooperate. Safety protocols evolved continuously. Every release of gas, every biological introduction underwent rigorous review. Unknown interactions posed risks that could set progress back decades. Caution was not seen as delay, but as preservation of effort. The planet would respond on its own timescale, regardless of human impatience. By the end of this phase, Mars was undeniably changing. The sky held a faint blue tint at certain angles caused by increased scattering. Frost patterns shifted seasonally, and temperature records showed a clear upward trend. Yet standing on the surface still required protective equipment and sealed habitats. The vision of walking freely under an open sky remained distant, but no longer unimaginable. Plans for the next phase were already underway, focusing on accelerating oxygen production and long-term atmospheric retention. New technologies, based on advances in materials science and energy storage, promised greater efficiency. Biological research aimed to expand the range of organisms capable of surviving outside protected zones. Each proposal was grounded in data collected over decades. Terraforming Mars in 2120 was not about completion but commitment. Every generation inherited a partially changed world and the responsibility to continue. The planet demanded humility because its scale dwarfed individual lives. Progress was measured not in headlines but in graphs, slowly trending upward. And as preparations began for broader ecological introductions, the planners knew that the next steps would test assumptions in ways not yet fully understood. Because the moment life began to interact more freely with the open environment, the planet itself would start to respond in unpredictable ways, shaping conditions that no model could perfectly anticipate, and forcing those involved to reconsider how much control was truly possible, and whether the emerging balance would favor continued transformation or require a pause, while new patterns revealed themselves across the surface and beneath it, where unseen processes were already unfolding beyond the reach of direct observation. And the story of this world was only beginning to diverge from every projection made before. As the transformation advanced, the next stage unfolded with a mixture of confidence and restraint, shaped by everything learned so far. Atmospheric pressure had reached a threshold, where exposed water could persist for hours instead of minutes, and this alone changed operational planning. Equipment no longer needed to be fully sealed at all times, and emergency exposure protocols became less extreme. These changes reduced logistical burden and allowed wider exploration beyond established zones. The atmosphere remained dominated by carbon dioxide, but nitrogen introduced from processed regolith began to stabilize pressure. Nitrogen was critical because it acted as a buffer gas, slowing atmospheric loss and supporting future biological processes. Extraction systems operated continuously, separating nitrogen compounds, locked in minerals, and releasing them gradually. This was energy-intensive, but essential for long-term stability rather than short-term warming. Temperature averages continued to rise, though unevenly. Equatorial regions warmed faster, creating stronger circulation patterns. Winds redistributed heat and moisture, carving new surface features. Dunes shifted more rapidly, and sediment transport increased, altering landscapes mapped decades earlier. Continuous remapping became necessary because assumptions based on static terrain no longer applied. The planet was becoming dynamic again. Attention turned increasingly toward atmospheric chemistry. Trace gases played outsized roles in heat retention and ultraviolet filtering. Introducing them required precision. Small imbalances could cascade into unintended cooling or excessive warming. Computational models ran constantly, updated by real-time data streams from surface stations and orbiting platforms. Decision-making became a collaboration between human judgment and machine analysis. Biological expansion entered a sensitive phase. Microbial life had proven resilient and predictable, but more complex organisms introduced new variables. Lichens and moss analogues, engineered for cold tolerance, were tested in semi-open environments. These organisms required minimal nutrients and contributed to oxygen production while binding soil. Their slow growth matched the planetary timeline, avoiding rapid ecological disruption. Radiation exposure decreased incrementally as atmospheric thickness increased. Measurements showed meaningful reductions, though levels were still higher than Earth norms. This allowed longer surface excursions with lighter protective equipment. Psychological benefits followed as settlers experienced greater freedom of movement. The ability to work outside for extended periods strengthened connection to the environment, reinforcing long-term commitment. Water management evolved from containment to distribution. Channels were reinforced to guide seasonal flows into reservoirs, preventing erosion and loss. Evaporation increased with temperature changes, necessitating adaptive storage strategies. Subsurface aquifers were tapped carefully to avoid collapse or contamination. Water was treated as both a resource and a shaping force, influencing climate locally. Dust interactions with climate received renewed attention. Warmer temperatures increased atmospheric lifting, creating more frequent storms. However, higher humidity caused particles to clump and settle faster, shortening storm duration. This balance reduced the likelihood of global dust events that once threatened power generation. Understanding this interaction validated earlier climate projections and built confidence in predictive models. Energy infrastructure expanded alongside environmental changes. Solar arrays were redesigned to function under partial dust cover and diffuse light. Nuclear systems continued to supply baseload power, while experimental fusion prototypes began contributing small amounts. Excess energy was stored chemically or used for atmospheric processing, ensuring minimal waste. Energy abundance enabled flexibility in planning. Governance structures adapted to reflect the changing environment. Regulations shifted from survival-focused restrictions towards sustainability guidelines. Environmental impact assessments became standard for every new project. The planet itself was treated as a stakeholder, with metrics designed to quantify planetary health. This approach integrated science, ethics, and policy into a unified framework. Construction methods changed as well. Materials produced locally reduced reliance on imports. New composites tolerated temperature swings and radiation while remaining lightweight. Structures were partially buried or shaped to manage wind and thermal flow. Architecture responded to the environment rather than resisting it, reflecting a philosophy of coexistence. Long-term atmospheric retention remained unresolved. Gas loss to space continued despite progress. Proposals for large-scale magnetic shielding gained renewed interest as technology advanced. Smaller regional field generators demonstrated effectiveness, suggesting scalability was possible. These experiments informed designs that could one day protect the entire planet, though implementation remained distant. Education and training emphasized adaptability. Skills, once specialized, became broadly taught, enabling cross-functional teams. Environmental monitoring, engineering, biology, and logistics overlapped in daily work. This flexibility ensured resilience when conditions shifted unexpectedly. Knowledge transfer across generations remained a priority, preserving continuity of expertise. Economic exchange evolved internally. Value centered on contribution to planetary systems rather than accumulation. Credits reflected energy production, ecological restoration, and infrastructure maintenance. This discouraged exploitation and promoted stewardship, aligning economic incentives with terraforming goals. External trade focused on knowledge rather than material goods. Cultural traditions adapted to new cycles. Seasonal changes, though subtle, became markers for communal events. The first persistent clouds inspired ceremonies recognizing planetary milestones. These rituals reinforced shared purpose, bridging scientific endeavor and human meaning. The environment shaped culture as much as culture shaped intervention. Scientific uncertainty remained constant. New feedback loops emerged as biology interacted with climate. Oxygen production increased marginally, but methane fluctuations introduced complexity. Monitoring detected occasional spikes, prompting rapid response teams to adjust production rates. This vigilance prevented instability and reinforced respect for planetary scale systems. Health research continued addressing low-gravity effects. Infrastructure incorporated artificial gravity zones, using rotation to support long-term well-being. Medical data informed lifestyle guidelines, ensuring populations remained healthy across generations. Adaptation focused on minimizing harm rather than altering fundamental biology. External observers noted visible changes from orbit. Albedo variations indicated shifting ice and vegetation analogs. Spectral analysis confirmed atmospheric composition changes aligning with projections. These observations validated decades of effort and attracted renewed interest in planetary engineering elsewhere. Mars became a reference point for applied planetary science. Despite progress, ethical debates persisted. Questions about altering a pristine world resurfaced as changes became undeniable. Counter-arguments emphasized that Mars had always been dynamic, shaped by forces beyond control. Terraforming was framed as participation rather than violation, guided by knowledge and restraint. These discussions influenced transparency and documentation practices. Waste management reached near closed-loop efficiency. Every byproduct fed another process, minimizing environmental footprint. This efficiency reduced strain on planetary systems and supported expansion without proportional impact. The principles developed here informed sustainability models beyond Mars, demonstrating scalable solutions. Exploration extended farther from central zones. Mobile habitats supported longer missions, gathering data from diverse regions. These expeditions identified microclimates suitable for accelerated biological trials. Diversity of conditions allowed comparative studies, refining terraforming strategies. The planet revealed complexity that challenged earlier assumptions. Communication systems adapted to increased atmospheric interference. Signal propagation changed, requiring recalibration of networks. This adjustment improved redundancy and reliability, ensuring connectivity across growing settlements. Infrastructure evolved alongside the environment, maintaining cohesion. By this stage, the concept of a finished planet had been abandoned entirely. Mars was understood as an evolving system, requiring perpetual engagement. The goal shifted from completion to balance, ensuring habitability without erasing planetary character. This philosophical shift influenced long-term planning. Preparations began for broader ecological integration. Insects and small aquatic organisms were studied for potential introduction decades ahead. Their roles in nutrient cycling and ecosystem stability were evaluated extensively. Nothing would be released without exhaustive testing, acknowledging irreversible consequences. As conditions improved, interest grew in expanding open-air zones. Experimental domes were removed in limited areas, testing exposure tolerance. Results informed design of transitional environments, bridging sealed habitats and open terrain. These spaces allowed gradual acclimation, reducing risk. Weather prediction improved with increased data. Localized forecasts guided daily operations, enhancing safety and efficiency. The ability to anticipate storms, temperature swings, and water flow marked a new level of environmental integration. Mars was becoming predictable again. Reflection on progress emphasized patience. Each gain represented years of coordinated effort. Failures occurred, but informed better decisions. Terraforming proved less about dominance and more about listening to planetary response. This mindset shaped the next generation of planners. As the atmosphere thickened, sound carried farther, altering perception of space. Subtle changes like this affected human experience, reminding inhabitants that transformation touched every sense. The planet felt less alien, though still distinct. Long-term archives preserved records of every intervention. Future generations would inherit not just a changed world, but a detailed account of how it was shaped. This transparency ensured accountability and learning across centuries. With these foundations, laid attention turned toward accelerating oxygenation without destabilizing climate. New approaches combining biological and industrial processes were proposed. Trials would begin cautiously acknowledging uncertainty. The next phase promised greater change and greater risk. Standing on the surface, watching thin clouds drift across a warming sky, planners recognized that Mars was no longer just being altered, it was beginning to participate actively. Feedback loops strengthened, interactions deepened, and the planet responded in ways that demanded humility. The story continued, not as a linear plan, but as a dialogue between intent and environment, unfolding step by step across decades yet to come.